Okay, so we are live and we are about to start our session on atomic structure. And as I said, we will. Okay, so we are live and we are about to start our session on atomic structure. And sorry about that. A few technical issues with my second window open and the volume on, so a bit of feedback there. But it looks like we're all set to go. And so atomic structure, and I guess a good place to start would be to give a short sort of historical perspective of our understanding of atomic structure and how it has evolved over the last sort of 2 millennia, we should say. If we look at this very handy chart, it gives the impression that our thoughts about the atom and matter and what makes up matter started so a little over 200 years ago. In fact, our idea of the atom and how it forms, or rather is a constituent sort of basic building block of matter, goes back to the ancient Greeks, certainly in the written record. And so Democritus had the idea that there was this indivisible particle, which he called the atom, which made up all substances. And this idea pretty much held sway way right up to and beyond the early 1800s. Dalton pretty much had the same idea there. So as we can see here, you've got Dalton, who drew upon the ancient Greek idea of the atom, which sort of means indivisible. And his theory stated that atoms are indivisible. Those of a given element are identical. So that was John Dalton's contribution. And it wasn't for another 100 years before it was shown that the atom is indeed divisible, that it contains subatomic particles. And this was sort of achieved by J.J. Thomson and others who worked at about the same time, who devised the experiments. J.J. Thomson reached the right conclusion, I guess, and so gains most of the credit for certainly discovering the electron, based on work on cathode ray tubes. From his discovery of the electron, he decided, came up with a model that suggested that you had a sphere or a cloud of positive charge, which is this purple sphere here, and embedded in that positive charge, you had electrons. So these electrons were studied or sort of placed, spread throughout this sphere or cloud of positive charge. But it wasn't very long before someone came along and showed that actually this wasn't the case. And the experiment that showed this was Rutherford firing alpha particles, or also known as helium nuclei, at gold leaf, and noticing that the vast majority of the alpha particles just passed straight through. Now, this can only be consistent with the idea that the atom is mostly empty space. What Rutherford discovered, however, was that the positive charge was all concentrated in a very dense nucleus, somewhere in the middle, incredibly small nucleus where all the positive charge was. How did he know this? Because some of the alpha particles, which are positively charged, encountered the nucleus and were deflected from the straight path, so suggesting that there was a source of positive charge that was repelling these positively charged alpha particles, or helium nuclei. Okay, so that was the next evolution in our understanding of the atom. And I guess a better sort of iteration of that model would have been Niels Bohr's idea that rather than the electrons being in these fixed orbits around the nucleus, as suggested by Ernest Rutherford, the electrons were actually, according to Niels Bohr, in sort of quantized or specific sort of orbits with specific energies a set distance away from the nucleus, and he called these shells. Moving on another couple of decades, or perhaps sort of less than 2 decades, to the late 1920s, and we have Erwin Schrödinger postulating what is currently the accepted model of the atom. Again, with that positive nucleus right in the middle of our atom, but surrounded by a cloud of electrons. So the electron can't be pinned down to a specific location. We know the energy of the electron, we can't say exactly where it is. All we can do is work out the probability of finding the electron in a given regional space. And this given regional space, you'll very shortly find out, is known as the orbital. Okay, so the electrons inhabit orbitals, each orbital containing a maximum of 2 electrons, and this is the result of solving the wave equation for electrons. So electrons, in a sense, are behaving not as particles, but as waves, and in so doing, it becomes very difficult to say exactly where you will find the electron in the atom. So this is a possible history of our understanding of the atom and how our ideas have evolved, and I guess some experiments that have led to our to our understanding of how the atom is organized as far as its subatomic particles are concerned. Okay, but what do we need to know as far as the AS spec goes? So if my screen seems to have frozen for some reason. I'm going to have another go at sharing it with you. If you bear with me for a second, stop sharing and try again. Okay, so on your screens, I do apologize for that technical glitch, but on your screen, you should see a copy of the AS specification, and we're looking at atomic structure. And of course, we're going to be looking at some of the overlap between AS chemistry or A-level chemistry and what you've already done at GCSE or IGCSE in some cases. So we're going to be starting by looking at what isotopes are, as well as looking at different subatomic particles and some of the properties. And what we've just done in our introduction is look at the different models of the atom and how these have evolved over time. And then over the course of the lesson, we will look at some definitions that you're required to know. So relative isotopic mass and relative atomic masses. And also, we're going to be looking at the use of mass spectrometry to determine isotopic masses and the relative abundance of different isotopes of an element. Okay, so once we've done that, we'll also do some basic relative formula mass calculations as well. Okay, so that is what we've got in store for you. As I said, if you have any questions at any point, please do stop, and please do use the chat box and do stop me, and I will pause to answer your questions for you. Okay, so on to atoms then. So we've just seen that atoms consist of subatomic particles. I'm sure you knew that already. And of course, these are protons and neutrons, which are found in the nucleus. Okay, so we've got protons and neutrons in the nucleus, and in orbitals outside of the nucleus, you've got electrons. And in a subsequent live session, I will go through the rules for populating these orbitals with electrons for any given element. Okay, but for now, we can say that electrons which are found in orbitals, these orbitals are in the different energy levels, or we can still call them shells, outside of the nucleus. Okay, so some properties of the subatomic particles that we still need to know. And these are the relative mass and, of course, the relative charge. The actual masses in kilograms or grams are incredibly small numbers, and so for convenience, we choose to discuss the masses of these subatomic particles relative to each other, sort of setting the relative mass of the proton as being 1. So we complete our table. The relative mass of the proton is, of course, 1. The relative charge of the neutron is also, so the relative mass of the neutron is also 1, and the relative mass of the electron is a very small fraction of the mass of the proton. It's about 1 over 1,836, the mass of the proton. And when we talk about the relative charge, we know that the proton is positively charged. It has a relative charge of +1. The neutron, as the name suggests, neutral, so not charged. The name suggests there that it has a 0 relative charge, so not charged or uncharged, and the electron has a charge of -1. Okay, so this is something that you would have come across at GCSE. On some GCSE courses, you may have seen the relative mass of the electron described as negligible or sort of almost 0. Again, it's not a non-zero number. The electron has mass, and that mass is about 1 over 1,836, the mass of the proton. Okay, so important to remember that. So moving on then to sort of one of the first definitions that you're required to know at AS, and again, perhaps depending on the GCSE course, you will have come across this before, is the term isotopes. And we'll look at how we can work out the masses of isotopes of the same element very shortly. But isotopes are, of course, atoms of the same element. Okay, so how do we know that they are atoms of the same element? They have the same number of protons. Okay, so what makes one isotope different to another? Well, it all comes down to the number of neutrons. So isotopes are atoms of the same element, but with different numbers of neutrons, and as a result of having different numbers of neutrons, they will have different masses. Okay, so if we look at our definition and what you need to have in your definition, they are atoms of the same element with different numbers of neutrons, and as a result of that, they will have different masses. Okay, so that's what we're required to say in answer to the question, what is an isotope, or what are isotopes? Okay, then down in the sort of second half of that screen there, you can see some examples of isotopes. I've got 2 elements, and I've got some common isotopes of those elements. We've got hydrogen, which is the simplest element in our periodic table. And of course, hydrogen has an atomic number of 1. And that atomic number 1 is shown there. And if I write in the atomic number for that isotope of hydrogen as well, so we've got the proton number 1. But what we've got that is different between these 3 isotopes is the mass number there. Okay, so you've got 3 different mass numbers because each of those isotopes of hydrogen has got a different number of neutrons. Okay, so how many neutrons are there for each isotope? Well, the way to work it out is to subtract the number of protons from the mass number. Okay, so in the case of the protium, or the hydrogen atom with mass number 1, it will have, we use that, it will have 0 neutrons. So that 0 plus 1 proton gives you the mass number 1. Deuterium will have 1 neutron, and tritium will have 2 neutrons. Okay, so you've got protium, or the hydrogen atom as we know it. You've got deuterium, which is the hydrogen isotope with a mass number 2, and you've got tritium, which is the hydrogen isotope with mass number 3. Okay, and below the isotopes of hydrogen, we've got some isotopes of carbon as well. So the most common and most abundant isotope of carbon is, of course, carbon-12, and carbon-12, as we'll see very shortly, is of great importance to chemists as a standard for measuring masses. Carbon-13 is an isotope of carbon that you will come across in the second year of A-level study, because it is very useful as an analytical technique, as a spectroscopic technique for solving structures of mostly sort of organic compounds. So carbon-13 NMR, and carbon-14 we might have encountered in the context of radioactivity and half-lives. Carbon-14 is the isotope that is used in radiocarbon dating. So if you're a paleontologist or an archaeologist who digs sort of ancient artifacts or bones out of the soil, you will be measuring the amount of carbon-14 left in those specimens, and using the half-life of carbon-14, which we know, you can work out or estimate quite accurately how old that object is. Okay, so these are all isotopes of the same element. They have the same number of protons, as you can see there. What they differ in is the number of neutrons, and therefore the mass numbers, or the masses. Okay, so at this point, I will so take a quick look to see if there are any questions for me. We very quickly scan through the chat window. Okay, so no questions at the minute. Let's have a little look here as well. Okay, good. Okay, so we'll carry on with our work then. So that is isotopes. The next thing to consider is what happens to an atom when it loses or gains an electron. Okay, so again, thinking back to your work at GCSE in bonding, you would have come across the concept of the ion. So we need to know how an ion is formed. We also need to know how an ion differs from an atom. Okay, so what I didn't point out previously, and we've seen some isotopes here, which are we can consider atoms, is that they are all uncharged. Okay, so the atom is not a charged species. So the proton and the electron will cancel each other out, or the numbers of protons and numbers of electrons in an atom will always cancel out, so that the atom itself is a neutral species. Now, moving on to ions, we've got an imbalance or a difference in the number of electrons versus protons. Okay, so for any element, the number of protons isn't going to change, but what might change is the number of electrons. So an element might lose electrons. Typically, metals will lose electrons. Non-metals will gain electrons. Okay, so you can therefore have more electrons than protons, or more protons than electrons, and this will result in a charge on the particle, on the atom. So an atom that acquires a charge is known as an ion. So it says here that ions are charged particles formed when an atom loses or gains an electron, and this results in a difference in the number of protons and electrons. Okay, so we've got some examples of ions in the table shown here. So here we've got a sodium ion, and then we've got a sulfide ion, and we've got an aluminium ion. Okay, and in each of the three cases, we can use our understanding of the number of protons each of these elements has, and so the number of electrons, to work out the missing missing quantity. So for the first row, we've got a sodium ion, and we know that sodium has got 11 protons. Its atomic number 11. If it has a plus charge, it must mean that there is one more proton than electrons, and so the number of electrons for that sodium ion is going to be 10. Okay, and we can use the same logic, we can apply the same logic to the sulfide ion. The sulfide ion is made from sulfur, which is element number 16, which of course has got 16 protons. Now, in this instance, you've got a charge of 2 minus, and so that is telling you that you've got 2 more electrons than there are protons. Okay, so the number of electrons for the sulfide ion is going to be 18. And then to complete our table, we've got aluminium. Aluminium is a metallic element. It's element number 13. That means it's got 13 protons. And we can explain the charge, the 3 plus charge, by the fact that it has lost 3 electrons, so that there are 3 more protons than there are electrons. And so you've got a 3 plus charge. Okay, so 13, which obviously tallies with what we know about the atomic number for aluminium. Okay, so that is the ion, or these are examples of ions, and ions are always, they are charged species, they have a plus charge or a number of integer values of a positive charge, or they are negatively charged. Okay, so moving on to the masses of atoms. Again, as I alluded to sort of in the introduction, or just after the introduction to the session, we're dealing with incredibly small masses of atoms and subatomic particles. And so it makes sense to measure or deal with these masses by using a standard and quoting in terms of the mass relative to that standard. Okay, so the standard that chemists have chosen to use and hasn't always been carbon-12, but is carbon-12 is sorry, to get my words right. So carbon-12 is the standard chosen against which the masses of all atoms are measured relative to. So whatever the element, you're going to measure the atomic mass relative to the mass of carbon-12. And indeed, the relative isotopic mass, or the mass of an isotope, is the mass compared to 1/12 the mass of a carbon-12 atom. Okay, so 1/12 the mass of the carbon-12 atom being exactly 1, because the mass of the carbon-12 atom is defined as exactly 12. Okay, so an important definition to know. So this is the mass of an isotope compared to 1/12 the mass of carbon-12. And the relative atomic mass, which takes into account the different isotopes that make up the element, is the weighted mean. So if you're going to work out the relative atomic mass, which we will be doing very shortly, you need to take into account the different isotopes that make up an element, but you also need to take into account the proportions of the isotopes making up the element. Okay, so for instance, we saw carbon-12, carbon-13, and carbon-14 on the previous page. Well, carbon-12 is the most abundant isotope for carbon, so well over 99% of carbon isotopes are carbon-12, and so that will contribute the most to the relative atomic mass of that element. Okay, so we'll be looking at very shortly how to calculate the relative atomic mass using the natural abundances of these different isotopes. Okay, so we need to find the weighted mean mass compared to 1/12 the mass of a carbon-12 atom. Okay, so how do we calculate how do we calculate the weighted mean? Well, let's have a look at the sort of data that you would be faced with. So on this screen, we're looking at the mass spectrum for an element, and this element is boron. Okay, so it says here in the question, what does the mass spectrum of boron look like? The mass spectrometer itself is an instrument that measures the mass of atoms or even molecules very accurately. So what you do is you inject a sample of your element or your molecule into your mass spectrometer. It is ionized and it acquires a positive charge, which then travels towards a negatively charged plate. Now, all of the positively charged particles that are formed in the ionization process are all have the same kinetic energy. So they are accelerated to the same kinetic energy. And so what they do when they're drifting towards a detector is that they'll travel at different speeds depending on their mass. Okay, so you know the equation for kinetic energy, which is half mv squared, right? So ke is equal to half mv squared. If they all have the same ke, and therefore their velocities will depend on their masses. Okay, so the quicker they travel, the smaller the mass will be, or larger the velocity, the smaller the mass will be. The slower they travel, the smaller the velocity, the higher the masses will be. Okay, so the mass spectrometer will sort out these particles by their mass, and this is the output from the mass spectrometer into which a sample of boron has been injected. And as you can see on the x-axis, we've got the mass divided by the charge on the particle. So the mass is m, and the z is the charge. Okay, so we've got the m over z values here, and these are almost always +1 because it is very difficult to ionize an atom so that it has a charge of +2. You can see it sometimes, but the vast majority of cases, you're going to have a charge of +1. And so the m over z value is actually telling you about the mass of the isotope in question. So if we look at the mass spectrum for boron here, there are two isotopes. You've got an isotope with mass 10, and we've got another isotope with mass of 11. So the m over z values of 10 and 11. And also on the y-axis, we've got the relative abundance. Now, the relative abundance is sometimes or usually shown as a percentage, but that isn't necessary. It can be any number, it could be any scale here. So the important thing is that you know what the sort of the maximum, what the sum total of the abundances is. Okay, so in this instance, we've got a relative abundance for the isotope boron 11 being 100, and the relative abundance of boron isotope 10 being 23. So the sum of these two abundances is 123. So if we're going to calculate the weighted mean, so I've just noticed that my screen sharing has gone slightly awry. I'm going to again to try and connect my screen share with you again. I to pause sharing for a moment and try this again. So okay, so it looks like, yep, we've got our screen back. I do apologize for the technical glitches. It's our first session back after a very long summer break, and so we are having some sort of technical issues, which hopefully will all be resolved in time for our next live session next Saturday. But on your screens, you should be seeing the mass spectrum of boron, and as I said earlier, you've got the relative abundances of 100 for boron mass number 11, and abundance 23 for boron mass number 10. Okay, so if we're going to calculate the weighted mean for this element, so the weighted mean mass for this element, so the relative atomic mass of boron, we will need to take the isotopic number, or rather the mass isotopic mass 10, and multiply that by its relative abundance, which is 23 for 10, and boron 11 is 100, and then divide by the total of the abundance, so 23 plus 100. So if you do that and to punch your numbers in right into your calculator, you should end up with 10.8, which is our relative atomic mass for boron. Okay, and we will be looking at some more worked examples very shortly. Now, obtaining the relative atomic mass is very important because we can then go on to use it to calculate the relative molecular mass or the relative formula mass of simple molecules as well as substances with giant structures. Okay, so let's have a look at how we can do that. So a little refresher, this is something you will have encountered at IGCSE or GCSE. So if we look at water, water has the formula H2O, so 2 hydrogen atoms bonded to an oxygen atom. Now, I'm sure you can all tell me that the mass number of hydrogen is 1 and the mass number of oxygen is 16. But let's assume that you didn't know this. Where would you find this information from? You would need a periodic table, and I've got one on your screens, and there is hydrogen with its mass number of 1 shown there, and we've also got oxygen down here with its mass number of 16. Okay, so we should be able to work out the relative atomic mass of our rather the relative molecular mass of water using the relative atomic masses for hydrogen and oxygen. Okay, so in doing so, you're going to be adding 1 to 1, so these are the atomic masses of hydrogen, to 16, and that of course gives us 18 as the relative atomic mass, so rather relative formula mass or relative molecular mass of water. I should point out that while the relative formula mass and relative molecular masses are used interchangeably, in fact, you want to use the relative molecular mass for simple molecules such as water or benzene, which is shown sort of down here, and to use relative formula mass for ionic substances, things with giant structures. Okay, so we've got here calcium carbonate, and we've also got hydrated copper sulfate down there. Okay, so very quickly working out the relative formula mass of calcium carbonate. You've got calcium, which is 40 off the top of my head, and you've got carbon, which is 12, and then you've got 3 times 16 for the 3 oxygen atoms. That's 48 plus 12, which is 60, plus 40, which gives us 100. Okay, and if we very quickly do the same for benzene or C6H12, we've got here, sorry, did I say it's not benzene at all? It is actually hexene. I am sort of all over the shop this session. C6H12 is not benzene. Benzene is C6H6. Do forgive me for that slip. So C6H12 is an alkene, and that alkene is of course hexene, and hexene has got 6 times 12 for the number of carbon atoms we've got, and add to that, you're going to have 12 times hydrogens. Okay, so 6 12s is 72, and to that, if we add 12, we're going to have 84 as our relative molecular mass. Okay, so that is how you would go about calculating relative molecular masses and relative formula masses using the relative atomic mass. Okay, and I will leave you to work through well, maybe we should work through it together. So copper is has a relative atomic mass of 63.5. Oops, didn't mean to change screens. Go back, and 63.5 for copper. A GCSE rounded up to 64. And sulfur has a relative atomic mass of 32.1. And of course, you've got our oxygens. We've got 4 times 16. And we've just worked out the relative molecular mass of water, which is 18. So if we've got 5 moles of water of crystallization, we could have 5 times 18 in our calculation. So plus 5 times 18. Okay, so we now my mental arithmetic is okay at the best of times, but in this instance we've got quite a large set of sort of sums to do. So let's use my calculator, which is 18 by 5, which is 90. I hope so. Yeah, it is 90. So 90 plus 64 plus 32.1 plus 63.5 should give us 249.6 as our relative atomic mass. Okay, so relative formula mass, I should say, and again, do forgive me. So relative formula mass of copper sulfate, hydrated copper sulfate, is 249.6. Okay, so we're nearing the final third of our session, and that usually means that we tackle some practice exam questions. These are taken from AS papers from 2016 and 2017. I have also uploaded these onto the website, so for our subscribers, do nip over to the website at your leisure and do sort of work through some of these problems. I would typically post these problems on the morning of the session so that you've got a chance to have a look at them and perhaps have a go at them before joining in the session. Now seems to be a good time to pause and check to see if there are any questions at all. I'm going to very quickly switch over to YouTube to see if there are any questions. Let's have a quick look. There is a question here from someone going by the name Mads Myers. Could you change the screen to very good. So hopefully the screen issues have been sorted for you. But in answer to the question, why is carbon-12 used as the standard? Carbon-12 is a very stable isotope, and we have it in very huge or very large abundance and can measure its mass very, very accurately. So in answer to the question, why is carbon-12 used as a standard? In the past, and I think that it was only chosen as a standard in the 1960s. In the past, oxygen was used as a standard. I believe hydrogen has been used as a standard before. Hopefully that answers your question, Mads. Good. So if there don't seem to be any other questions, so what we will do is look at these practice exam questions on from the AS papers, Breath in Chemistry. So this is paper 1 of the OCR A-level course, the AS level course, I should say. And so let's have a look then at this from the 2016 AS paper. Okay, so we will look at the relative atomic mass calculation for copper using that mass spectrum sort of given to us. But before we do that, there is quite a nice calculation leading up to it in part A, which we can look at. So we're told that a 20p coin contains copper and nickel, and we want to state the similarities and differences between the atomic structure of isotopes of the same element. So similarities, of course, would be that they have the same number of protons and neutrons. Sorry, not neutrons, electrons, same proton numbers, and same number of electrons. And if we are talking about the differences between isotopes, of course, the one important difference is that they have different numbers of neutrons. Okay, so that's sort of a very nice, sort of straightforward sort of starter to this question. So here in part B, we've got an example of a mass spectrum that allows us to see what the isotopes present for copper are. So we've got an isotope with mass 63, or M over Z 63, and another with M over Z 65. And we are told what the percentage abundances are for each of these isotopes. And so we can work out what the relative atomic mass is. And we are asked to do this to 2 decimal places. And so we will be keeping to that instruction. Okay, so how do we do that? So we've got isotope number, isotopic mass 63, and that has a relative abundance of 69.17. And we've got the other isotope, which is 65, with abundance 30.83. And if we divide that by 100, okay, so the isotopic abundances should add up to 100 in this case, with the relative abundance is being given as a percentage. And so if we punch these into our calculator, we are expecting a number somewhere between 63 and 65. So if you get a number that isn't between 63 and 65, you know that you're definitely wrong. Okay, so let's do this. 63 times 69.17. Let's try that again. 3 multiplied by 69.17. And to that, we're going to add 65 times 30.83 and that should give us a number which we then divide by 100, and that gives us 63.62 in this question. Okay, so we've got 63.62, which in a sense is what you would expect. You've got isotope with mass 63 being very abundant, being almost 70% of the mixture, whereas 65 is only 30.83, about 31%. And so you would expect the mass to be much more closer to 63 than to 65. And so we've got, if 64 was the halfway point, this is towards 63. Okay, so let's look at the next question then. Okay, so there we go. So our next question is to do with, again, copper and the percentage by mass of copper. Again, this is a sort of a calculation that you will see very shortly in our session on quantitative chemistry, which will be in another couple of weeks' time. But let's have a go at doing this anyway to see the sorts of skills you're required to have coming in from GCSE, which you can apply to this question. So it says here that one coin has a mass of 5 grams and contains 84% by mass of copper. Okay, so we can immediately work out what 84% of 5 grams is. And if I work that out, let's try that again. Okay, so it's 4.2 grams. So 4.2 grams of copper in our coin. So it says calculate the number of copper atoms in one coin. The way to go about this is to first of all find the number of moles of copper in that coin. So the moles of copper is going to be 4.2 grams, which is the mass, divided by the relative atomic mass of copper, which you can find in your periodic table. And here is our periodic table. The first row of the transition metals is, there we go, copper, atomic number 29, and mass number 63.5. And so we go back to our calculation and divide 4.2 by 63.5. Got. And so here we go. If we gives us 0.0661. We've got 0.0661 moles, right? Now, we know how many particles are in a mole of anything. We know that 1 mole is Avogadro's constant, which is 6.02 times 10 to the 23. Therefore, if we have 0.0661, then it will simply be Avogadro's constant times 0.661. Okay, so if we do that, 6.02 23. So we've got a very, very large number here. We've got 3 significant figures. We've got 3.98 times 10 to the power 22 atoms. Okay, so that's our answer to 3 significant figures in standard form. Good. Now we've got time for one more question. So we'll skip the question on bonding for another session when we come to bonding. What we want to do is have some more practice at calculating the relative atomic mass using mass spectrometry data. So looking at mass spectra and using the abundances and using the isotopic abundances for our calculation of relative atomic mass. So this time round, we've got another element, and this element is magnesium. And magnesium, you've got the isotopes magnesium 24, so magnesium 25, and magnesium 26. Okay, so these are our isotopes of magnesium, and these are the percentage abundances. So 10 plus 11.01, that's about 20. That's 21.01, and 21.01 plus 78.99 should give us 100%. Okay, so let's look at the first question. The first question requires us to complete the table. The species causing the peaks in the mass spectrum are 1+ ions of magnesium, so the magnesium atoms lost 1 electron. Complete the table to show the number of protons, neutrons, and electrons in each 1+ ion of magnesium. Now, despite having an ion of charge 1+, we know that the number of protons hasn't changed. Nothing in the nucleus has been affected by the loss of the electron. So you can have the same number of protons for each of these isotopes. Now, magnesium is atomic number 12. We can confirm that looking at our periodic table. And here we go. There's magnesium atomic number 12. And so for the number of protons, we're going to have 12 in each of these boxes. All of the isotopes will have the same, of magnesium will have the same number of protons. Where they will differ is in the number of neutrons. Okay, so for the isotope with mass over Z of 24, it will have 12 neutrons, because 12 and 12 gives 24. For M over Z 25, you're going to have 13 neutrons, and you're going to have 14 neutrons for M over Z 26. Now, we know that each of these has a charge of 1+, which means it's lost 1 electron. So in all cases, you should have 11 electrons altogether to give you the charge 1+. Okay, so that's the table completed. And then in part 2, we're asked to calculate the relative atomic mass of the magnesium sample, giving our answer to 2 decimal places. Okay, so let's look at the data given to us. We've got M over Z 24, which has an abundance of 78.99. Confirm that, it does indeed. And then we have the isotope 25, which has abundance of 10 exactly, 10%. And add to that, we've got isotope number 26, M over Z 26, I should say. And that has an abundance of 11.01. Okay, so we're looking at sort of a number somewhere between 24 and 26, just so we can sort of quickly troubleshoot any errors in our calculation. Of course, all of that divided by 100. Okay, so if we punch that into my calculator, so we've got 24 times 78.99 plus 25 times 10, which is 250, plus 26 times 11.01, and if we divide that by 100, we should get number 24.32, 2 decimal places we're asked to give our answer to. Okay, so that's 24.32. Okay, so that completes our session on atomic structure. At this point, I'm going to pause again to very quickly check that we haven't got any questions on YouTube. Okay, so no questions since we last checked, and there are no questions on Zoom either. So looks like we're all set to sign off. I hope you've enjoyed this session on atomic structure. This is going to be a regular Saturday evening 5 p.m. slot for us. For those of you who were watching last year, we were on a Sunday. We've moved things to a Saturday, so 5 p.m. on a Saturday. Before joining in a session, do have a look at the questions and the material I've posted on the website if you're a subscriber. And also do go away and practice and tackle some practice questions. So go away and look at the AS papers and see if you can find some more calculations on relative atomic masses using mass spectrometry information. As usual, it's been a pleasure to host everyone, and if you do think of any questions to ask me, please drop me a line at boostrevision.com. I'll be more than happy to hear from you. I look forward to seeing you in 2 weeks for a Year 12 session. If you're a Year 13 watching today, I will see you next week, same time on a Saturday. Thank you very much for joining in. It's been a pleasure. I'm Dr. Arusu signing off. Thank you.